Hello everyone and welcome back. Today we are solving MCQs from aldehydes and ketones. This topic is famous for tricky exam questions, so I have picked some special examples for you. These will help you understand the core concepts and get you completely ready for the exam. So let's get started. The first question is based on the series of reactions. You can see that there is a cyclohexanone molecule which is in turn attached to a secondary alcohol like this. This is treated with PCC. PCC stands for pyridinium chlorochromate, which is an oxidizing agent. It will oxidize the secondary alcohol to ketone. So here you are going to get a ketone. What about the ketone present here? No change with respect to this. It will remain as it is. So this is our product 1. So P1. Now, this is treated with iodine in NaOH. This combination is an oxidizing agent and it will selectively oxidize aldehydes or ketones with methyl attached. What I mean is, if there is a ketone attached to methyl group, it will break the bond over here and this methyl will change to iodoform. What is iodoform? CHI3, nothing but a yellow precipitate. Then what is the fate of this molecule? It will oxidize to the corresponding carboxylic acid. Therefore, what product are we going to get? The ketone will be untouched. You write down that as it is. Since the bond will break here, you are going to get a salt of the carboxylic acid, but it's understood that it will be hydrolyzed to the corresponding carboxylic acid, and the byproduct is iodoform CHI3. So you can see that there are two products, P2 and P3, right? And P3 is the yellow precipitate. This is the yellow precipitate. What about this one? This is P2. It's very important to identify the products here because you can see further the P2 is going to react with sodium borohydride. So what happens when this reacts with sodium borohydride? You should know that this is a reducing agent and it selectively reduces ketone but not the carboxylic acid. So when you reduce the ketone using sodium borohydride, you're going to get a secondary alcohol. What about the carboxylic acid? That will remain as it is like this. But because you are heating this in acidic medium, what will happen whenever there is an alcohol and acid heated in presence of a catalyst, then it's undergoing esterification. You can see that this hydroxyl group will attack here and we are going to get the ester. How to write the structure of this bicyclic ester? Because you already have a cyclic structure within the molecule and these two are undergoing intramolecular esterification. So you are going to form one more ring. If you are forming one more ring, that means what? It is a bicyclic structure. You can see that the oxygen will be here as it is. Here the carboxyl group is there and they are attached to each other. There is a better way of representing this molecule. How do you do that? The bicyclic structure can be written like this. So this is the final product P4. Just try to identify the correct structure. Where do we have it? You can see this is 6 and 5 membered. You can ignore this. So here we have a 6 membered. This is also 6 membered. How is it 6 membered? Just check here. 1, 2, 3, 4, 5 and 6. Here also 1, 2, 3, 4 and either you take these two carbons or these two carbons. Doesn't matter. So 6 carbons. So these two are same structure. Hence, the correct option is option B. The next question is based on the concept which is the most frequently asked concept in the exam. The first reaction here is ozonolysis followed by the aldol condensation. How did I know this? Because you see that the products given here are either hydroxyaldehyde or unsaturated aldehyde compound. So you can guess that the product is from the intramolecular aldol condensation. You can see that the benzene ring is retained and where the ozonolysis is happening, the ozonolysis is happening over here. And this will form an aldehyde. And what about here? You can see there are two CH2 groups. So CH2, CH2 and then here we are going to get the aldehyde. Why are we getting aldehyde? Because of the presence of the hydrogens over here. If there are some alkyl groups, then we would have got the ketone. So this will be our product A. When A is treated with base, upon heating condition, we are going to get alpha beta unsaturated aldehyde, as it is a intramolecular aldol condensation. What happens in intramolecular aldol condensation? The first step is the base will abstract the proton from the alpha carbon over here, and then it's going to form a carbanion. This carbanion will act as a nucleophile because it is a electron rich carbon. So you can see this is the carbanion form. So since we have electrophilic carbon over here, it's going to attack the electrophilic carbon. Then it will undergo addition. So once it undergo addition, we have to get the beta hydroxy product. That is the first product in aldol condensation. So how to write the product? Very easy. Count the number of carbons from here to here. So 1, 2, 3, 4, 5. So we are going to get a 5-membered ring. On this carbon, right, there is a aldehyde. You write that. And check if it is beta hydroxy. If this is a principal functional group, this is alpha, this is beta. This is beta hydroxy aldehyde. Now what happens? Since there is a heating condition, finally it will undergo elimination. This is condensation because we are removing a water molecule. So from alpha carbon, you're going to remove the hydrogen from beta hydroxyl group, and then you are going to get alpha beta unsaturated aldehyde like this. The benzene ring will remain as it is. So this will be our final product B. Compare the structures of the products given in the options. You can see this is alpha beta unsaturated, but look at the position of the CHO. It's supposed to be here, not here. So eliminate this. Now check this one. This is exactly what we got as a final product. Therefore, the final answer is option B. In this question, you have to identify the final product B. While these reactions look complicated, I'm going to make them simple. First, identify the functional groups present in this bicyclic molecule. There is an aldehyde and then there is a ketone. And it is treated with the vicinal diol, nothing but ethylene glycol in a catalyst, that is dry HCl. The moment you see this reaction condition, you should know that a diol reacts with aldehyde to form an acetal, and it reacts with ketone to form a ketal. Since it is a vicinal diol, we are going to get a cyclic acetal or a cyclic ketal. But which one are we going to get? Acetal or ketal? For that, you need to know the reactivity of the aldehydes and ketones. By now, you know that aldehydes are more reactive than ketones. Because of this, the aldehyde will react with the vicinal diol and form a cyclic structure. So how to write that structure? You can write it in one step. Just follow my lead. You can see there is a carbon over here. So this is the first member of the ring, and the 2 oxygen atoms, you write down that as it is, and the 2CH2 will remain as it is like this. So we are getting a 5-membered acetal molecule like this. What about the methyl group here? Not changed. You write down that as it is. So this is our product A. What is the second reaction condition? So there is a hydrazine followed by KOH in ethanol. Before you start writing the condensation product, just understand why this KOH in ethanol is given, because this condition, reaction condition, is nothing but it's a Wolff-Kishner reduction. In Wolff-Kishner reduction, what do? We reduce the ketone, whatever the ketone group is there, to hydrocarbon. That means it will reduce to CH2. There is a complete reduction. So what product are we going to get now? The cyclic part, whatever is there, it will remain as it is. Here we are going to get CH2. The methyl group is also not changed. The acetal part will also remain unchanged because this is a ether. It will not get reduced in Wolff-Kishner reduction reaction. Therefore, this is the intermediate we are getting. Why so? Because we have not done the hydrolysis part yet. When you do hydrolysis part, the acetal will undergo hydrolysis and you are going to get back your aldehyde as it is like this. The methyl will also remain like this. So what did we do? If you just summarize the overall reaction, you see first we have protected this aldehyde because aldehydes are more reactive than ketones. You did your favored reaction, that is Wolff-Kishner reduction, and then you have done the deprotection of the aldehyde. This protection in deprotection is commonly done when there are more than one functional group in the molecule. So this is our final product B, and compare the structures here. You see this doesn't have any aldehyde group, so you can eliminate this. Now check here, there is a ketone and aldehyde is reduced. Not correct. Check the C option. You see the aldehyde is there and the ketone is reduced. So this is correct. Therefore, the correct option is option C. Now let's solve a complex question from the ketones chapter. This also clubbed with the amines topic. The first reaction is between a ketone and a secondary amine. It forms product X. X upon treating with the methyl bromide followed by hydrolysis forming two products Y and Z. There is a hint given here. The Z upon reacting with Hinsberg reagent forming white precipitate which is not dissolved in KOH. That means what? Z is a secondary amine. You can also see in the reactant also there is a secondary amine. So preferably it's the same amine. And we are doing some reaction with respect to this ketone. So the end product must have a ketone. So it could be either B or C. So let's check that. So if you already know the reactions, you can write them directly. If you don't know, you can still predict it. How so? When a ketone reacts with the secondary amine. The secondary amine here is N-methyl ethanamine. It's going to form enamine. This you might have learnt in amines chapter. What is enamine? How to generate it? So do it step by step. The lone pair of electron present on nitrogen will attack here because it is nucleophile and this is electrophile, and the carbonyl double bond will undergo addition. And how to write the product? You can see this will become O minus. O minus in turn will take up this proton and it will become OH. What about here? This will have methyl and ethyl like this. So is this X? No, not yet. Why so? Because a carbon attached to two electronegative elements like oxygen and nitrogen is not so stable. So what happens here? The lone pair will shift here and the OH will get removed. Why so? Because you have acidic medium. So this in turn will get protonated and it will help this OH to remove as water. So you are going to get enamine. So en because there is a carbon nitrogen double bond like this and this is an amine. What should be the charge on nitrogen now? Plus because it is tetravalent. Now we can regenerate the catalyst here. How so? By removing the proton over here. So you can see that the double bond will be formed over here and this will become amine. This would be our product X. The X is treated with methyl bromide. The methyl bromide furnishes the methyl as an electrophile. So the carbon-carbon bond is more preferred. Therefore, when the nitrogen donates the lone pair, it will give those electrons through this carbon and form the bond between this carbon and this carbon. So how to write the product? Make use of the arrows, how you have written here. So the double bond will be formed over here. And since nitrogen is tetravalent, write the positive charge. The electrons are given to the methyl and the bond is formed. The bromine is a good living group. It's living as a bromide. Now, you can see this is imine. Imine upon hydrolysis. This is a very simple step. You just have to write the oxygen over here and you got back your ketone. And what is this? This will be product Y. What about the Z? As I told earlier, Z is a secondary amine. So this is the secondary amine we will get back like this. And when secondary amine react with Hinsberg reagent, it forms a white precipitate which is not soluble in the KOH. So all these statements hold good for the given reactions. So this is our product and it is present as option B. Therefore, the final answer is B. The last question is quite simple if you already know the order of reactivity for aldehydes and ketones and the reaction of sodium borohydride with the carbonyl compounds. So in this question, you have to arrange the given molecules in the decreasing order of the reactivity towards the reducing agent sodium borohydride. Sodium borohydride furnishes hydride ions. That means what? It is a nucleophile. So how easily this nucleophile will attack the carbonyl compound depends on how electron deficient is this carbonyl carbon. If it is electron rich, the attack of the nucleophile will be difficult. If it is electron deficient, the attack of nucleophile, that is hydride, will be much simpler. So between aldehydes and ketones, we know that aldehydes are more reactive than ketones towards the sodium borohydride as they are electron deficient due to the presence of hydrogen, and also there is a less steric hindrance. So the hydride will attack easier. Therefore, what happens? Its reactivity will increase. You can see in ketone, both are electron donating and also there is a steric hindrance. It will become difficult. So just look for the molecules where there is an aldehyde. There is an aldehyde here and aldehyde here. So 1 and 4 must be more reactive than the given ketones. So 1 and 4 being highest. Where do we have it? You can see in option A. Therefore, the right option is A. However, let's justify this answer. So 4 is more reactive than 1. Why so? Because there is an electron withdrawing group which withdraws electron, making this carbon more electrophilic. So what happens to the hydride attack? It would be much easier. Therefore, 4 is greater than 1. In case of 1, there are electron donating. That's why it is less reactive. Then we have molecule 2. You can see there is a ethyl and then there is a bulky group. That's why it is less reactive as compared to 1. Why is this the least reactive? Because more the bulkier group over here, the attack of hydride will become much difficult. Hence, this will be the least. So this is how you have to compare the reactivity of the molecules. In the next session, I'm going to discuss certain questions from carboxylic acids and their derivatives. If you like my video, please like, share and subscribe the channel. Thank you.